This is section 16.3, double integrals in polar coordinates. It turns out that it's really useful to do double or even triple integrals, and we'll be using mostly these functions that have inputs as the plane and outputs of a number. But often the regions and shapes that we're dealing with are not boxes. Often they're round or, basically anything other than a box, and you have to figure out how to think in other coordinates other than rectangular coordinates. So we'll see how to do that in this section. We'll see how to figure out the bounds of integrals when we're dealing with like round objects. We'll figure out how to find volumes using polar coordinates, and then we'll do areas with polar coordinates. So let's just recall a little bit of polar coordinates. If you have the point, like say you have a point out here, you can describe its location by saying how far over you went to get to it and how far up you went. That's the point x, y. But you can also describe where it is by just saying how far from the origin it is and what angle it is from the positive x-axis, and then you would call it r theta. So for example, the rectangular point 5 minus 5 is over to the right by 5 and down by 5. So it's like 45 degrees down from the positive x-axis. So its angle in polar coordinates is minus pi over 4. Its radius, r, the distance from the origin, you can find with the distance formula, or if you remember how like triangles work from geometry, this is 5 root 2 from the origin. So this point, 5 minus 5, is the same point as the point 5 root 2 minus pi over 4. Similarly, so in this case, like 5 minus 5 is easier. We will usually use polar coordinates when it's easier to use polar coordinates. Here, what's x squared plus y squared? Well, the main useful thing that we deal with in polar coordinates is circles, and circles with a radius. So this is a circle with radius 3. So how do we figure that out using polar coordinates? Well, we say x squared plus y squared is r squared, because here's this right triangle. So in polar coordinates, this is r squared equals 9. Or even better, we can just say that r equals 3, and it will still work out for us. So if you have to deal with points that are best described on a box, then you use rectangular coordinates. If you're working with things that are better described using radius and angle, then you use polar coordinates, and that's just about it. These are the like conversions between polar and rectangular coordinates. So let's just practice the thing that we will actually need, which is you're going to have a region. And if you remember, the regions in the xy plane, the information of that region will end up in the bounds of the integrals. So we're trying to get all the region information, all the geometry information about where the integral is happening up into the bounds of the integral. So like this box, we would say, well, x goes from 2 to 5. And in an integral, this would be the x bounds. And then y goes from 2 to 6. Now, for this region, like that's a literal rectangle, so rectangular coordinates are good for that. This region is a half of a circle, so we should expect that polar coordinates are better. And in fact, it is. This one, here's r equals 0, and here's r equals 1, and here's r equals 2. So r is going from 0 to 2. And then over to the positive x-axis is theta equals 0. And then theta goes up to pi over 2 and all the way around to pi. This is powerful because if you tried to describe this half circle in rectangular coordinates, you would have to say something like x goes from minus 2 to 2, and y goes from 0 to the top of a circle, which is like square root of 4 minus x squared. If you get to choose between having these bounds, 0 to 2, 0 to pi, or these bounds, minus 2 to 2, 0 to square root of 4 minus x squared, you should pick the nice one. Okay, what about this region? It's a triangle. Probably we should say that we'll just use x bounds first, that x goes from 0 to 5. And then the bottom and top will both be a function of y. This bottom is y equals 0. And this top is y equals 6 minus something x, some slope. I guess it goes down 6 every time it goes over 5. So 6 minus 6/5 x. It's just the equation of this line. So x goes from 0 to 5. Y goes from 0 to 6 minus 6/5 x. This one, it's more like a box situation, so like it has straight lines and right angles, and so we use rectangular coordinates. Where this one, if I tried to write these bounds in rectangular coordinates, it would be a complete disaster. In polar coordinates, it's easy. The radius, the lowest radius is 3, and the highest radius is 5, and all the angles are represented. So depending on what radius you have, or not what radius, depending on what region you have, you should either use rectangular or polar coordinates, whichever one is easier to use. And this section is all about how do we actually finish the problem once we've decided that we're going to deal with a region that is best in polar coordinates. Okay, so here's an integral, and the idea that you're supposed to have, geez, sorry, I'm sure that's distracting in this time of day when I'm like rubbing my nose constantly. The idea you should have from the previous sections is that the bounds of the integral describe a region in the xy plane. And then we think of this function, I mean the function is just 5 right now, but we think of that function as determining the height of a surface. And I just pressed the Windows key, which is not helpful. Okay, so what's going on here? Well, there's some region in the xy plane, and then above it is just 5 units of height. So we've got a solid that's a cylinder with height 5. And the base is, well, x goes from -2 to 2, and y goes from so the bottom half of a circle to the top half of a circle. So this is in the xy plane. So it's a cylinder with the base of a circle of radius 2 and the height 5. Using geometry, the volume of a cylinder is just the base times its height. The base is a circle of radius 2, and the height is 5, so it's 20 pi. Now, that's like a really nice way to do this integral, to say, oh, this integral is a volume, and I'll just go find the volume. If you don't notice that, you could still do it. You could just do the integral. So you would say, okay, I'll do the y integral first, because it's on the inside. It's 5y from -4 minus x squared to 4 minus x squared. Plug those in, and I'm going to get, whoa. So the thing I just wrote down was this inner integral. So I still need the dx on the outside. Okay, I'll have 5 square root of 4 minus x squared minus the same thing. So I'm going to end up with 10 square root of 4 minus x squared. I don't know if this is a flashback for you from Calc 2, but this is a trigonometric substitution because I have no x on the outside to make this into a u substitution. So I'll let x be 2 sine theta. That way I'll get 4 minus 4 sine squared theta, which I can actually deal with. Dx will be 2 cosine theta d theta. And then the bounds, x was going from -2 to 2. So what is theta going to? Well, if x is -2, that means we need sine theta to be -1, and that happens at minus pi over 2. If x is 2, that means sine theta is 1, and that happens at pi over 2. So we end up with, once we've done the substitution, it's going to be a theta integral from minus pi over 2 to pi over 2. I've got a 10. This is square root of 4 minus 4 sine squared theta. Dx is 2 cosine theta d theta. And this looks like it's working fine. So I'm going to have 10, 2, and another 2. So that's 40. And then I have cosine theta and another cosine theta. So I have cosine squared theta d theta. Goodness, what a mess. The point of this question is that it told us to begin, and the point of doing the first half of this integral is to say, like, oh my gosh, this is awful. Like, it's just a cylinder with the base of a circle. Like, whatever our final plan is for doing this problem, it should not be this hard. And we could finish it and we would get the right answer, but I'm not going to. Instead, we're going to switch to polar coordinates. So let's look at the region again. The region in the base was just a disk with radius 2. And the bounds in polar coordinates are, well, what are the r bounds? The r bounds go from 0 to 2. And what are the theta bounds? Well, it goes all the way around. So the theta bounds go from 0 to 2 pi. So this seems way better. There's not going to be any weird square roots. And whenever you end up doing a trig substitution where you're letting x be sine theta or cosine theta, that's a clue that maybe you should have been doing it in polar coordinates to begin with. So let's figure out how to... we've decided that when we have a circle as the base, that we'd be better off changing coordinates to come up with polar coordinates instead. So let's get the details of like how we do that. I think I'm decided that I don't like this page. Well, I don't like these like blanks to fill in, because this is just the way that I've been thinking about this the whole time and that I've been portraying it to you the whole time, is that if you're finding the integral, the double integral over the region R, here's the region R, this box, of f of xy, and here's this surface z equals f of xy, dA. I think of this as, well, all you need to do is slice up R into little pieces, which will be the dA. And here's like a little slice, dA. And then you go up to the region, and you get kind of like a really tall box of volume. And if you add up all the height times bases, then you're adding up all the volumes. Now it turned out, oh my gosh, why is this here? Now when we slice up the base this way into a grid, what we get is that this little box, dA, was dx dy, or the little base dA was dy dx. And the order, all it affected when we were doing integrals earlier was it affected what was going on in the bounds. But dA is not automatically just d first variable, d second variable. It worked out that dx times dy was the area of a little box. But when we slice up a region a different way, it might not be just the two differentials multiplied by each other. So I'm skipping that, like, that fill in the blank, but that was the point. So what we do instead when we have polar coordinates is, like, I'm going to do the same thing. I have a region in the xy plane. But instead of slicing it up into a grid that's like an xy grid, which will give me little boxes that have area dx dy, instead I'm going to slice it up this way. Using, these are rays, and like this, using arcs. So let me put the original functions there in a different color. So say we're looking at this region in the xy plane. I could slice it up into boxes dx dy, but now I'm instead considering, what if I split it up the polar coordinate way using arcs and rays? Now my little shapes here, my little dAs, are no longer nice rectangular boxes. Instead, my dA looks like, well, I've got a tiny change in angle here, d theta, and out here I've got like two arcs of different sized circles, and the difference here is dr, and I'm looking for this area. Here's dA. Now, I think you should see that in this case, the area of that little region is not dr times d theta. There's no reason that it would be. Like, d theta is a little bit of angle and dr is a little bit of radius. It wouldn't make sense to multiply them. The reason we multiplied dx times dy was because dx was the base of a little rectangle and dy was the height of a little rectangle. So instead, I need to use a geometry argument to figure out what dA should equal in this case. Okay, well, what does it equal? So we need to be able to figure out like how long this is. If we could figure out how long this is, and we make really, really tiny slices, then I could multiply this length times dr, and I would feel like I had a pretty good approximation for what dA was. Okay, well, what is this? This is some fraction. Let's just give it a name. I don't know. I kind of want to call it dc because it's like a little bit of the circumference. So dc is some fraction. It's some fraction of the circumference. So here's the circumference. What fraction is it? Well, the whole circle would be 2 pi angle, but we only have d theta of the circle. So I have this much d theta out of 2 pi of the circumference, which is 2 pi r. So actually this length here is the 2 pi's cancel, and I get r times d theta. So what do I get as my dA? My dA here is now this like height, dr, times this width, which is r d theta. So dA in polar coordinates is r dr d theta. This is very difficult for students to remember because most students don't have a geometric understanding of what dA even means. That dA is a little bit of volume, or that dA is a little bit of area. D just means a little bit of, right? So a little bit of area. dA being dx dy or dy dx seemed to make sense because like it was a double integral, but I would really invite you to think of dA as being base times height when you're in rectangular. In polar coordinates, it's a little bit more complicated. Instead of like base times height being d theta times dr, instead it turned out that it's r dr d theta. There's this extra term here, so you just need to not forget it. Yeah, so the area of a single shaded sector is dA is r dr d theta. So what is this good for? What this is good for is that if you have a function of, and you're thinking of it in polar coordinates, then you can do the double integral of the function, and then instead of dx dy or dy dx, you can put r dr d theta. And then you can put theta bounds on the outer integral, and r bounds, I don't know, like an inner and an outer function maybe, on the inner integral. So this is what your integral will look like. So let's do that to find the volume of this cylinder, which we already know the answer is 20 pi, but let's just do it. So you look at this and you say, rectangular coordinates look like a disaster here, so I'll turn it into polar coordinates. This is our region. And this region I got from just the bounds, the x bounds and the y bounds. I'm going to write the region in a different way. Instead of it being x goes from -2 to 2, am I like sitting in front of this? No, okay. X goes from -2 to 2, and y goes from like crazy function to other crazy function. Nah, I don't like that. Instead, I'll use r goes from 0 to 2, and theta goes from 0 to 2 pi. And changing into polar coordinates, you actually just change the bounds, because you're just changing the way you think about the region. You leave the function completely alone, and then you change dy dx, which was one way to write dA, into a new way of writing dA. which is r dr d theta. D theta is at the end here, so I'll put the theta bounds on the outside. R is on the inside, so I'll put the r bounds on the inside. And I have a new integral. And I think you can see already that this integral became much easier. But let's do it. So the outer integral is going to sit here and wait for us to finish the inner integral. The integral of 5r dr is 5/2 r squared from 0 to 2. When I plug 2 in for r, I'll get 10 here. So I'm going to have the integral from 0 to 2 pi of 10 d theta. And that's 10 times 2 pi, which is 20 pi. So for this cylinder, the best way to do this is to realize that this question is asking you like an 8th or 10th grade geometry question. But if you don't realize that, and you normally won't, the next best way to do it is to realize, oh look, the bounds are describing a circle, so I'll switch everything into polar coordinates. And if you can do that like thinking outside the, oh my god, thinking outside the box is just like a horrible pun here, because we're like switching from rectangular coordinates, so you think outside the box. Okay, well, that thinking outside the box of just not doing the exact question that's given to you and saying like, nah, I'll have this other perspective instead, that's the really powerful thing here. So let's do a couple of these. It might only be one, actually. No, there's 2. Okay, find the volume under this surface. So again, we're thinking of a surface as being a function that has an input of x, y, and an output of a height. We'll put this surface above this region. And when you look at this region, you should be like, nice circle. I'm doing polar coordinates. X squared plus y squared less than or equal to 4 is the disk of radius 2. So you could describe this in terms of x and y, but no thanks. Instead, I'll describe it in terms of r and theta. So let's go. The volume is going to be the double integral of the function times dA. And then the trick is, once we've decided polar coordinates, that decides what dA is, and that decides what bounds we choose. So dA is r dr d theta. I'll just leave this function alone. And then the r bounds appear to be on the inside, so I'll go 0 to 2. And the theta bounds are on the outside, so I'll go 0 to 2 pi. Now you should notice that this integral is not possible right now, because it's an r and theta integral, and the function is made of x and y. So if there are x's and y's in your integral, like in your integrand, you need to change them into r and theta. But that's not too bad, because we know that x squared plus y squared is r squared. And there were other things in that box, I think on the first or second page, that would let you convert between x's and y's. So you need to get all these to turn into r's and thetas before you can continue. But not too bad. This is 16 minus r squared. Then to actually do this integral, I think of there being an inner integral and an outer integral. The inner integral looks like I have a nice u substitution here. I can let u be 16 minus r squared, and then du will be minus 2r dr, and I have r dr, so I can put minus a half du is r dr. Then I can change the bounds. R goes from 0 to 2. If r goes from 0 to 2, then u will go from, we'll just plug in 0, and I get u is 16. Plug in 2, I get u is 12. So I'm going to have integral from 0 to 2 pi, integral from 16 to 12 of minus a half square root of u du d theta. This integral I can actually do. So I'll make the power 1 bigger, divide by the new power. The power was a half, so now it'll be 3/2. That's pretty good. I'll need to plug in 12 and 16, which is pretty unfortunate, actually, since I'm out of space. But I'll just keep going down into this problem, I guess. So when I plug in 12, remember the 3/2 power is 1.5 copies of the number. So I need to do 12 square root of 12 and 16 square root of 16. And it's minus a third, both of those. So minus a third, 12 root 12, plus a third, 16 root 16. And this is all d theta. This integrand has no theta in it, so the integral from 0 to 2 pi is just going to multiply by 2 pi. So if I can just finish like simplifying this, then I'll be in good shape. Square root of 12 is 2 square root of 3, and square root of 16 is just 4. So I can get a pretty reasonable answer here. Is it best to distribute it or factor something out? I think I'll just factor some stuff out. Yeah, so I'll factor out the third. And then I'll write that this is 64 minus 24 root 3. It's a pretty reasonable way to write the answer. There's no single correct way to write the answer of this, but you should simplify it enough that it's like possible to tell that the answer is positive, I think would be a good cutoff. Okay, let's try to do the last example here. So the last example says to try to find the area of the polar regions r equals 3 cosine 3 theta. Okay, let's go get a picture of what r equals 3 cosine 3 theta looks like. In this situation, because it's just a function with two variables, it's going to be some region in the plane. Desmos is our best tool. So let's head over to Desmos. We're looking at r equals 3 cosine of 3 theta. Notice that you spell out theta, T-H-E-T-A, if you want Desmos to figure out what's going on. So here's 3 cosine 3 theta. 3 cosine 3 theta is this neat little shape here, and it looks like it's made out of 3 symmetrical regions. So our answer is going to be, we'll just find the area of one of these regions and then multiply the result by 3. Well, how will we do that? It's not too bad. If you want to find an area, just like if you want to find anything, to find a thing, you should add up all the little bits of the thing. And now we have a new way to write dA, which is you can write dA as r dr d theta. Because I have a dr and a d theta, I can write this as a double integral. And then the trick is I just need to find what are the right bounds for that region. So what are the bounds for that region? Let's do this little loop here. Apparently the loop actually looks like this, but let's just do this loop. The bounds are, well, where does this start and end? The loop starts and ends where r equals 0. So let's try to find where that happens. It's 0 equals 3 cosine 3 theta. That means, okay, either 3 is 0, no, or cosine 3 theta is 0. Well, cosine 3 theta equals 0 at 3 theta equals, like when the angle is minus pi over 2 or pi over 2. Those are the easiest solutions. So the bounds for this little loop are theta equals minus pi over 6, and theta is pi over 6. So those are my theta bounds. I'm going to go from minus pi over 6 to pi over 6. And then I just need the r bounds. So how do I get the r bounds from the picture? Well, the r bounds are like, here's the lowest r down here, and then it's like the inner and the outer function. So the inner function is it goes all the way down to 0. The outer function is whatever draws this shape, which was r equals 3 cosine 3 theta. Notice that we keep all of the region information in the bounds of the integral. So you shouldn't be tempted to go in here where this r is and plug something in for r. Instead, all the stuff that tells you what the region looks like belongs in the bounds. So this is our integral setup, and now we can finish the problem. The integral of r dr is half r squared, except we're going from 0 to 3 cosine 3 theta. And just to remind ourselves, this is just the area of one of the little loops. So I'll call this the first area to try to remind ourselves to multiply it by 3 at the end. So this is my integral of, the r integral. The theta integral is waiting for us to get done with this, and we'll deal with it later. The 0 doesn't do anything here, so I'm just going to have 9/2 cosine squared of 3 theta from minus pi over 6 to pi over 6. Integral of cosine squared 3 theta. Okay, well, we can use a trig identity to simplify this. Cosine squared of anything is 1 plus cosine of double that thing. All over 2. And then we can do the integral. The integral of half d theta is half theta. The integral of half cosine 6 theta is half. And then integral of cosine 6 theta is a sixth sine 6 theta. And that's all from minus pi over 6 to pi over 6. And the good news here is that when you plug in pi over 6 into the trig part of this, you get 0. And when you plug in minus pi over 6 into the trig part of this, you get 0, because sine pi is 0, and sine minus pi is 0. So all this part goes away, and you just end up with 9/2 times half of pi over 6 minus half pi over 6. So what is this? This is 2/2 of pi over 6. So I end up with 9 pi over 12. It's a bunch of 3's. So it's 3 pi over 4. Neat. Let me make sure that's what I got when I did this before. Oh, crap. I made like this special effort to remember to multiply it by 3 at the end, and then I forgot. So that's the area of one loop, is 3 pi over 4. So the total area is 9 pi over 4 of all 3 loops. Let's look at the picture again to make sure that this seems reasonable. Pi is approximately 3, so this is approximately 9/4, so this is an area of approximately 2. So I want to look back at the graph and make sure that it looks like about 2 square units. On Desmos, this box is 1 square unit, like from 1 to 2, and can you see that from 1 to 2 and from -1 to 0. So like here's area 1 in this box. And then, yeah, there's about another 1, so this seems about right. Wait, no. It doesn't seem good at all. It looks like an individual loop has an area of 2. So I would expect my final answer to be like 6. Oh, yeah, that's right. Okay. The box that like one loop had an area of 2, and the overall area is more like 6. Okay, so it's right. Seems good. When you're done with a problem, you should really feel like it's okay for your answer to be wrong, and that it's okay to check your answer against some other thing to see like what's wrong with it. I'm not stressed out about my answer being off by a factor of 3. Like if that happened, I would go and find it and fix it. So hopefully you can also do that. But anyway, the takeaway for this section was that some integrals are way easier in polar coordinates than they are in rectangular coordinates. And that's usually when things are made of round shapes. If that happens, you change the bounds into polar bounds, and the dA part of the integral is now r dr d theta. So you just have to remember that r, this like factor that happens when you change coordinates. It has a name. It's called the Jacobian, and we'll have a section all about it later for other changes of coordinates. But you get r d theta. And then in our one example, you saw that in the integrand, you need to change everything into r and theta also. But the payoff is huge. It makes your integrals way easier, and it lets you handle shapes that you otherwise don't really have any chance to handle. So do some practice problems. I'll see you again for 16.4.